we're going to review similar rectangles in geometry. So if I give you a rectangle and I tell you that its width is 2 and its length or height is 5, and then I give you another rectangle and I tell you that these two rectangles are similar, and then I give you the width of the second one, you should be able to set up a proportion and find the missing length or height. A lot of times we call that the height. So there's two different ways we can do this. We can set this up as 2 over 5 equals 4 over L, or there's another way to set them up, which would be 2 over 4 equals 5 over L. That is a personal preference. Some of us like to compare within each rectangle. Some of us like to compare across from one rectangle to the other. If we do our cross products and solve a proportion, we should see we're going to get the very same answer. So 2 times L is 2L, 4 times 5 is 20, making L 10. This gives us the exact same cross products. 2 times L equals 5 times 4, or L equals 10. So these two rectangles are proportional because they both have the same ratio. 2 to 5 and 4 to 10. So we were comparing our width to our height and our width to our height or length. So if they're equal, they're proportional, they're also similar. Are all rectangles similar? A lot of people think so because they have 90-degree angles all the way around. That's not true. We also have something called a golden rectangle. And in golden rectangles, we have this rather odd phi that is a constant. It's very similar to pi, and its value is it's exactly 1 plus the square root of 5 over 2, or about 1.618. And this was used originally in photography because even way back in ancient times, they thought that if any rectangle could be put into a ratio of length to width or height to width, and it ended up really close to this value, it was pleasing to the eye. And if you look back at art and photography, when we finally got to that, in ancient times, the art, a lot of their drawings were in these proportions or in these ratios. So that today is not so true. The first photographs were probably 3 by 5s, and of course that's about 1 by 6. And now they've kind of disappeared, and we've got into 6 by 4s or 4 by 6s. That's closer to 1.5. So it appears we're moving away from the golden rectangle, and we don't see that taught very much anymore. But when you move into digital photography and even video filming, you're seeing something called aspect ratio. And you're doing the exact same thing there as ancient people tried to do with the golden rectangle. They're trying to find something pleasing to the eye. But it's so much easier now because you can stretch your pictures. You can stretch and get different aspect ratios. Your regular, normal TV aspect ratio is 16 to 9. But I think with new, bigger televisions, this is probably changing. It's probably not that anymore. And when you get into your lessons, you're going to find out what is more pleasing to the eye. The other thing aspect ratios do is let you fill the frame, if you will. You know, when we were taking pictures on a camera where we could not adjust that, you might have a person here and lots of space around them. That's where those people come in and photobomb it in the back. You can cut them out now with digital photography or with digital videoing. So you can stretch it and fill the frame. You can put it in landscape, but you have to be careful because I've seen a lot of these landscape pictures very disproportional. The people are not the size that they should be.
So now that we've learned more about ratios, let's go over a few terms you will need to know to understand math in the movies. The first term is aspect ratio, which is broken down into three main types in the movies: display aspect ratio, or DAR, pixel aspect ratio, or PAR, and finally storage aspect ratio, or SAR. For DAR, which is what we're going to be focusing on now, you look at the pixel width and relation to pixel height. And this we see everywhere, from movies all the way to your cell phone. The most common aspect ratio in DAR are 16:9 for movies and 4:3 for TV. Now, resolution is another thing that holds an important tie in movie making. The resolution of a screen refers to the number of pixels wide times the number of pixels tall a piece of media or a screen is. The most common resolution today is 1920 by 1080 pixels, and this also refers to high definition, or HD. Standard definition, or SD, refers to 480 by 720 pixels. These are basic industry standards, but any ratio is still considered a resolution. To visualize, we have included three versions of this video: one filmed in 4K, one in standard HD, and one in standard definition. Here we'll show you why resolution matters. You'll notice the difference between how sharp images are. The lower the resolution, the more pixelated it will be.
And our topic here is math in the movies.
Yeah.
What exactly did you do in your job, and did that require a lot of math, or how was that implemented?
Rather math oriented, right? You can't write code without knowing a fair amount of math. And that really culminated in the last 5 years, which is when the entire filmmaking industry flipped over from using film and analog media to sort of overnight moving to digital media. And then math got really important because everything at that point was digital, and by definition it's pure zeros and ones, it's purely mathematics, if you will. So that's kind of how that started. And now the whole film library isn't a warehouse, it's a data center with, I don't know, probably 100 petabytes of digital storage, and that's the film library. So, and now, you know, it's accelerating so quickly. If you remember this from last year, where if you think about 3D movies, right? Well, how did they start doing a 3D movie? Well, they had to build these gigantically complex, heavy, monstrous camera rigs with 2 cameras mounted on this rig, one shooting left eye and one shooting right eye, and then back in post-production they put it together and you have a 3-dimensional movie. And that cost about $30 or $40 million more than a 2D movie, just to get the 3D done. That wasn't that long ago, right? 3D movies really got going, right? But it was technically feasible, but it was so cumbersome, so expensive. Somebody said, multiple cameras and all that is just too hard. We need a mathematical way to derive the 3D without shooting 3D with multiple cameras. So we did a talk last year, if you remember it, down in the Commons called Computational Cinematography, where you can, with algorithms, derive the third dimension out of a film with math and with calculus. And that's the best part of the job, is making all that crazy. Everybody's brains are completely wired differently, and get them all to do something together in some really creative way. If you could do that in your career, I highly recommend it. It's really good.
Another number in the movie world is frame rate. To understand frame rate, we first need to know how a camera works. Every time a person takes a picture, several things happen. The first thing that happens is when the button is pushed down, the camera is focused. Then once focused, the camera meters the image to see how much light is available. Next, the shutter is released and springs into action. This moves a mirror and exposes the sensor to the light through the lens. This sensor collects the light, and a processor inside the camera turns the light data into a picture. With the video camera, this happens many times per second. Frame rate is also known as the frames per second, or a frame represents a picture taken. Most video cameras take 30 frames per second, but some cameras can do more than that, such as high-speed cameras, and these can take up to 10 million frames per second.